Thank you very much, Sandy, for this very kind, personal, and very generous introduction. It's a great pleasure to be here. I thank you and, of course, all the other organizers, Xiaowei, Atsushi, Rafa. It's, of course, a privilege to give this talk tonight and to tell you the story about super resolution and its basic principles. Now, we all know that throughout the 20th century, it was widely accepted, it was widely believed that the resolution of any light focusing microscope at the end of the day, for all practical purposes, is limited to about half the wavelength of light, or to be more precise, to a value of d, which is given by the wavelength divided by twice the numerical aperture of the objective lens. Now, this has been, so to speak, the general, basis of what people have saw that a light microscope is able to do. And, of course, many other techniques have been developed, as Sunny just mentioned, that have been, of course, very successful and very powerful, not at least the electron microscope. At the end of the 20th century, the gold standard in focusing light microscopy became the confocal microscope. And the confocal microscope was very important because it provided background suppression and it allowed us to do three-dimensional imaging non-invasively, especially in living cells. However, the spatial resolution of confocal microscopy was still limited by diffraction to typically about, say, 200, 300 nanometers. And so in this particular case, of course, we have an object, a set of proteins that it has been recorded confocally, but as you can see, it's not possible to see any details. Now, the development of STED microscopy at the turn of this century showed that you can really fundamentally overcome the diffraction barrier. There is land, so to speak, beyond the diffraction barrier. And so since we have developed this technique, I have now the option to show you an image that has been recorded with STED, and now you can see the details much, much better and see what it is. In fact, these are nuclear pore complexes from epithelial cell line of Xenopus laevis, and if you zoom in, of course, you see the details actually quite nicely. In fact, these nuclear pore complexes consist of 8 subunits, and why can you see them? Well, because the spatial resolution has been improved in this case over confocal by an order of magnitude. Now, an order of magnitude of resolution improvement really tells you a different story. That's very clear. I can't resist comparing it with the confocal microscope. And now you see that, this opens, of course, many, many possibilities. Now, as you may think, or you may think perhaps that in order to record such STED images, you require very complicated setups and systems. In fact, this recording was taken by a student in a student lab course setup. So if you think about that, then you will realize that the advancements that